Good afternoon. I'm Ed Palacio, and this is our last session for the CEWIT 2021 conference. In this session, we will hear three very interesting and relevant talks about applications of mobile device management and financial data, about forecast aggregation, and privacy breaches in cyber. Our speaker's presentation will be 20 minutes in duration, and there will be time at the end, 4 minutes or so for questions and answer. We will have the question and answer tab on the side. Make your questions over there. And with that, let me now present our first speaker. Our first speaker is Daniel Lasaga of Deloitte. His talk is going to be an application of mobile device management for anomaly and risk detection in financial data. Dan is a chief data scientist for regulatory and legal support products in Deloitte Risk and Financial Advisory. His skills and experience sit on the vertices of technology, communications, and management. He has former experience in a wide variety of industries, including manufacturing, utilities, banking, and commerce. His work has taken him in a wide arch, stretching from hands-on algorithmic programming to high-level interactions with decision makers. And with that, Daniel, let me introduce Mr. Lasaga, and you're on.
Thank you. Let me share my screen here, and we'll go into our presentation. So just a slight correction that the presentation we're going to go into here, and just let me know, can people hear me, and can they see my screen? Can I get a confirmation on that?
Yes, sir. We can see and hear your screen.
Great. Okay. So the MDN and the topic here is actually mixed density networks, which is a type of neural network. And the focus here on this talk is to discuss a particular approach to finding fraud and risk of fraud through anomaly detections and using density estimation and mixture density estimation with neural networks. So you gave me a great intro as to my background, so I won't cover this too much. But I'm a data scientist working with Deloitte for the past 7 years. So the background here is a lot of the work that I focus on is fraud oriented. And there's an issue with fraud that's very mercurial. Fraudsters, as soon as you identify a particular type of behavior, they'll change it to avoid detection. And then a lot of the systems we work in are very so this really renders a lot of more traditional approaches to classification of fraud or classification of behaviors insufficient. We don't have a lot of labeled data. And where we do have labeled data, it's scarce and hard to come by. And as soon as you get that labeled data, it's going to be old, right? It's going to be outdated. So largely what this leaves us with is a lot of unsupervised learning techniques. And one of the things just a brief contents of what we'll go over here. We're going to dive into a particular use case. And we're going to cover what has become very useful for us, which is turning things into one-class classification systems. And we'll cover that in brief, and then we'll cover the details of the reimbursement amount overage model that we're going to cover, and then the traditional neural network regression for one-class classification, and then mixed density networks, which is really our suggested approach here. And we'll do a demo and some questions at the end. So a brief covering what the use case that we have here, expenditure risk detection. And in this case, large organizations deal with employee expenditures. And this is a common source of fraud, waste, and abuse. So while policy rules can assist in identifying preventing particular errors, they'll never cover the entire base of fraud, waste, and abuse. So this is where machine learning can come in to really look at behavior in the data and identify unknown sources of fraud, waste, and abuse. The data set that we're using here, just in brief, this is from municipal expenditures from 2018, 2019, and relatively small data, 8,000 records around that have capture the amount, the type of expenditure, and the department that use the expenditure. In brief, this is this is an example data set that's publicly available on Kaggle. We have employed this in much larger, more complex systems effectively, and so I can give, if we have time, I can give some examples of that as well. So, like I mentioned, fraud is an interesting use case in that we don't often have great labeled data, and when we do, it's insufficient, and this leaves us largely in the unsupervised realm. So let's skip this. So, but one of the methods that we've found effective is to really turn unsupervised methods into redirecting it into a supervised model by looking at it in terms of a one-class classification system. In a brief, this really talks about thinking about periphery and the normal case and the periphery around it, and modeling what is normal in the system. So for our use case, what is a normal expenditure behavior? What is the normal amount conditioned on different on the different features in our case, department and type. So this is where density estimation comes in, and where regression can be a useful technique. While it's a supervised modeling technique, we're actually taking the supervised modeling technique, and we'll see how we can essentially work within an unsupervised context with a supervised modeling technique. So the model we're suggesting here is essentially, again, the model types, we're trying to model expenditures, and we're trying to model what normal expenditures should look like, conditioned on all the information that we have available in this particular data set, type, and department. So the manifestation of what fraud, waste, and abuse is going to look like in this is going to be unreasonably higher costs than the normal range of activity, given the inputs. So the examples here, you can see that there's different departments, so Department of Transportation and Department of Health, and different types of expenditures, meetings, parking, etc. And for each of these, there's going to be we're going to ask the model to estimate the range of normal activity. So we have these different curves, and they have from these different curves, we can estimate what the high tail, and if an expenditure is is far out in the right tail, this is where we're much more likely to find risk of expenditure, waste, and abuse. So now to take this a step further, we could take this and our input features and model a regression model. It doesn't have to be a neural network, but in this case, I'm giving an example of a neural network. The neural network is going to output a single estimate of what it thinks, given these inputs, the expenditure is going to be. This is, you can think of this is essentially the conditional average, or conditional mu. And you can, of course, optimize this using mean squared error and get a conditional mu. Now, what we mentioned is we're going to take this mu and we want to look at where the actual is essentially compared to the mu, the estimate from the model. And if it's far out in the right tail, if it's far out here, this is where we find risk. And we can use the condition, the commutative distribution function, and find out how far out in the tail it is. Problem with this is we then have where do we get sigma from? And sigma, given this model, is we can calculate it from the model standard error and get a sigma from that, basically a global sigma. So all inputs will have a conditionalized mu, but a global sigma. And the issue with that is that different, you can even see in this, different departments and type interactions are going to have different spreads. So the proposal for us is, and this has been a very useful model, is to look at mixture density networks, or at least look at, if not a mixture, look at a density network. So one, estimate sigma as well as mu in the outputs. And what this allows us to do is suddenly sigma is also conditioned on the inputs. So when we go to look at the actual versus the estimated expenditures conditioned on our inputs, we are looking at the sigma we are looking at a spread as well as the center of the range of activity in how we estimate risk. So as for results, what this ends up doing is getting a much more fine-tuned model in terms of where it finds risk. And this actually, from what we've seen, increases or decreases the false negatives. In other words, it's finding, excuse me, it's more fine-tuned to find where fraud is. It finds more fraud. You can see that in this, in the comparison between the left and the right. The left would be a traditional model that doesn't model sigma, so just a traditional regression model. And with a global sigma, the global sigma is, in this case, in this segment of the population, broader than what you get when you model with a conditionalized sigma. Here this is with the mixture density network. And so we're looking at fire department, and I think this is tuition. And the histogram is the actual spread, is the actual number, the spread of the monetary amounts for expenditures. And then this is the curve is the estimated model distribution. You can see this is much more tightly hewn to the actual data. And as far as results, and in terms of how much it finds, you can see that comparing the traditional regression model to the MDN, what you have is a prevalence of risk identified is higher. It finds more risk, almost double the risk in the MDN than the traditional neural network. And this also affects value, where when we can calculate the value, and I'll show this in a demo a little bit more, we can calculate the value, much more money at risk that it finds. An interesting side note is in this data, it found that the police department, and particularly the tuition risks or tuition reimbursements, expenditures, there was a lot of upside risk in the monetary amount and also in the number of claims that the traditional model did not find that the MDN found. So let me quickly go to a demonstration of maybe a little bit more detail on how this model works. How am I doing on time?
You have 7 minutes.
Cool. All right, so this is essentially the trained model, and I can show both the regular regression model and the MDN here. And I'll show a little bit how the one class classification works in this case, and how we get a risk scores and overpayment. So what I showed earlier was the fire department and tuition. tuition. So again, the data we're working with here is relatively simple as far as features. So you have municipal department, you have expense type, and then this is basically, is it using the regression model or is it using the mixture density network? So you can see, and then the other thing that's an input essentially is how much was the reimbursement. So, and you can see actual, and then this is the spread of normal activity. And then we basically marked one standard deviation above the mean, and above there is where we start to look at risk, or we calculate risk. So if I go to $3,600 for a reimbursement, I'll be right at the line in the municipal model, sorry, the regression model. And you see we're right at that one standard deviation. And again, this is a global sigma because we don't have an ability to condition in a regular regression model on sigma as well as mu. But when we switch this to the MTN, we'll see that this tightens up substantially. It's able to much more finely tune uncertainty and spread around that mean. And what was a relatively basically a zero risk and zero overpayment turns into an estimate of 71% probability that there's a problem, and over $600 of potential overpayment in that amount. And this $600 really comes from the amount over the standard range, standard deviation, combined with the certainty, the probability, which is kind of the area that you would calculate here. So, and if we go further out, you can see that the certainty is going to get much more, the amount is going to increase and the certainty is going to increase. We change this to 4,000. You can see this curve starts to approach 1, and we start to get really far out in the tail here. And so this increases to a 92% risk and a $1,700 overpayment potentially. So the interesting thing is that the part of the utility around using these mixture density networks and these density estimations as a way of modeling risk is that not only is it very flexible in how you can propose a number of these different problems, and I'll give a couple examples, but you can also change the distribution. So in this case, the model that we're looking at is really, it's using a normal, or technically a log normal curve to model off of. There is a model that we're doing that uses the same methodology, but it uses a negative binomial model because it's modeling the reasonable number of consecutive times an event happens. And there are other things that we've experimented with in terms of there's also work in this space on survival analysis that we're exploring, where we look at, say, a Weibull distribution, and we try and map out the longevity of something happening and estimate it using a very complex set of high dimensional inputs, and the output is going to be both the beta and eta of a Weibull distribution. So this is a very flexible and articulate way to model when you're specifically looking at the combination of an estimate of some flow point number as well as the uncertainty around it. Another example, and this is more similar to the model that we've looked at here, is in the healthcare space. We've used this. We're using this for estimating the range of claim payments for a healthcare claim, given the diagnosis and the any comorbidities on that diagnosis. And that, of course, is also a very high dimensional space. If you think about all the types of diagnosis you might get and interact those with all the types of comorbidities or other diagnoses that would coincide, you have a very, very high dimensional space. And this can if you have the compute power and the data, this can generate a very effective model. I think I can open up to questions now.
And how does the data shapes get affected by the volume of the sample points or the volume of the data that you received? Obviously, the more data you collect, how does that affect the model?
So of course, the more data you have, the more complex the feature inputs you can have. So 8,000 data points for this model works relatively well because we have a fairly small data space to work in. I think we cut out very low volume intersects, parts of the data where you don't have a lot of information. And generally that's what we do with the more complex implementations of this. But as naturally, as you get more data, you can build a more complex model input features, and it will generally perform better at estimating on the outputs. But it's a good question, and if you use this on data that you don't have enough of, you can potentially end up with some strange extrapolations.
And when you have multivariable data, like let's say for your fireman, your policeman, there's an amount of payment made, but then there's a number of courses taken or different types of courses taken. How do you normalize that?
If that data is available, you would include that. If you don't have that, then you're kind of going with the law of averages there, and you're saying, okay, we don't know the type of course that the policemen are taking, but we're going to estimate the average range using this technique, and that's where the sigma is actually helpful. If there is a much larger variety in the cost of courses that policemen are taking than the cost of courses firemen are taking, then that sigma can account for it.
Seeing none, Daniel, thank you very much for a very interesting talk, and please forgive me for getting your acronym wrong. I looked up the wrong acronym, but thank you. I found this as an extremely interesting discussion. And now we will be slowly going over to our next speaker. How do I do that? So now I'm back. Our second speaker will be Mr. Juntao Wang from Harvard University. His talk will be forecast aggregation via peer prediction. Juntao Wang is a fifth-year PhD student at the School of Engineering and Applied Science at Harvard University. He received his BS and his MS degrees in computer science from Shanghai Jiao Tong University. His research interests lie in developing more practical algorithms and mechanisms that leverage the collective intelligence of humans to solve challenging tasks. His algorithm has been adopted by replicationmarkets.com, which generates forecasts for the replicability and open social science studies using collective intelligence. And with that, Juntao, please.
Yeah, great. Let me share my screen. Yeah, could everyone see my screen? Yeah, thanks, Edward, for your introduction. Hi, everyone. I'm very glad to introduce our work forecasting peer prediction. So I hope you could enjoy my talk. So let's start with the development of the machine learning technologies. The machines are able to achieve superhuman performance in many tasks like image classification, regression, and gameplay. But how about forecasting the future events? This is a typical forecasting questions of interest. Will Amazon begin to accept any cryptocurrency for purchases before October 1st, 2022? Having an accurate prediction for this type of forecasting questions can greatly help decision makers to make high quality decisions. However, unlike the first three application scenarios, it is essentially difficult to have a purely machine approach to answer these forecasting questions. The reason is that the relevant information needed to answer a forecasting question usually have no fixed forms. It could be from news reports on TV, or from an earnings announcement, or just from daily observations. Meanwhile, we usually have no sufficient historical data to train the machine learning algorithms. So a promising approach to make forecasts is to rely on the wisdom of humans. Naturally, humans can serve as an efficient information aggregator to gather and process different information sources and generate reasonable predictions. Meanwhile, a machine or algorithm can be further developed to aggregate human predictions into more accurate ones, because now the information fed into machines take a well-structured form. So this is a typical one-shot human-machine hybrid forecasting system. We have a set of forecasting questions of interest, and we ask a pool of people to make predictions. And then we use the machine learning algorithm to aggregate these predictions into final predictions. This approach is also referred to the wisdom of crowds. Its effectiveness has been documented as early as 1907 in a competition of guessing the weight of oaks, and also in recent large-scale field experiments, the Good Judgment Project, about forecasting the geopolitical events. There are two main challenges in this human-machine hybrid forecasting system. First, in the forecast elicitation stage, the problem is how can we incentivize high-quality predictions? Unlike machines, which will do as instructed, human participants may provide random answers or manipulate their reported predictions for their own interests if there is no proper reward scheme set up to examine their prediction quality. Second, in the forecast aggregation stage, we want to know how to aggregate these raw predictions from people, because different people may have different expertise level. So we shall not treat their prediction completely equally in the aggregation. So when we know the outcomes of the forecasting questions, these two challenges are relatively easy to solve. For the elicitation problem, we could pay human participants how close their predictions are to the actual outcomes. By this way, it will be the best strategy for a rational human player to report the predictions they truly believe. And for the aggregation stage, if we have a partial set of forecasting questions with known outcomes, then we can model it as a standard machine learning problems. This is how most existing systems work. They pay participants after the outcomes of these forecasting questions are known, and they accumulate a history of each participant's predictions and the resolved outcomes to help aggregation for the incoming forecasting questions. However, this approach is both expensive and time-consuming, and sometimes even impossible. So in a recent project I joined, we aim to predict the replicability of 3,000 social science studies. And it's impossible for us to run the real replication experiments for all these studies. And we only have the capacity of running replication experiments for 300 of them, meaning that we can only know the outcome of 300 samples, which is very limited. So in this work, we want to address these two challenges without relying on the resolved outcomes. We want to pay forecasters and generate final predictions once the human forecasts are ready. And our solution is the surrogate scoring rules. There are a family of scoring mechanisms that provide an accuracy score for each forecaster, and they are robust to manipulation of the reported predictions. And a second feature of them is that they do not use any ground truth information. So ground truth information here refers to the actual outcomes of the forecasting questions. Instead, they rely on a forecaster's peers' forecasts to evaluate a forecaster's prediction accuracy. So these type of mechanisms that use a forecaster's peer forecaster predictions to evaluate the performance of a forecaster are called the peer prediction mechanism, which also gives the name of this talk. And our surrogate scoring rule is one of the peer prediction mechanism, and it focuses on eliciting probabilistic predictions, while others most focus on eliciting categorical signals like yes or no answers. And our main result is that for the elicitation stage, our surrogate scoring rule can serve as an effective reward scheme, and it will encourage high quality predictions. And in the aggregation stage, it will also help improve the aggregation accuracy because it will tell us which forecaster are more likely to be an accurate forecaster. And in the following, I will introduce these two problems one by one in detail. So first, let's talk about how to incentivize high quality predictions. Let's first see the standard approach to solve this problem when we know the ground truths. The standard approach is called the strictly proper scoring rules. Let's consider a simple forecasting question. Well, it's a rent model. We use Y to denote the actual outcome. The strictly proper scoring rules are functions of the reported predictions Qi and the ground truth Y. And it should satisfy this truthfulness property. So let's see. So suppose Pi is the prediction that agent I truly believe, and Qi is any other prediction. So this property says that the expected score from I's perspective, where Y is drawn from the belief of agent I, is greater if agent I report the prediction truthfully than it report any other prediction Qi other than Pi. So basically, this property guarantees that a rational agent who wants to maximize its expected score is willing to provide authentic predictions. And an example of the strictly proper scoring rules are the Barrett score, one of the most widely used strictly proper scoring rule. And it is 1 minus the quadratic difference between the reported prediction and the actual outcome Y. And it also reflects the accuracy. So let's see, suppose Y star is the true probability where Y is drawn from, then the true expected score of reporting Qi is equal to a constant minus the quadratic difference between the true probability P star and the reported prediction Qi. And more accurate prediction will get a higher score. And this property holds for other strictly proper scoring rules as well, but they correspond to a different divergence function here. So now we're clear how incentive is guaranteed when we can use the ground truths. Now we consider the forecasting elicitation problem without using the ground truths. We first consider a simpler setting where we can access to a surrogate signal Z of ground truth Y. Z is characterized by its error rate with respect to Y, which are just these false negative rates and false positive rates. And we suppose that we know Z and the error rates. If we directly plug Z as Y in the strictly proper scoring rules, then the resulting score will be biased. However, if we apply this debiased formula against the prediction QI and Z, and the debiased formula is a reweight of the original score, and the weight is determined by the error rate. So if we apply this carefully designed debiased formula, then we'll finally get an unbiased estimate of the true score. So by this way, we can score the accuracy of a prediction as if we are knowing the actual outcome Y. Now the remaining problem is how can we construct such a surrogate signal Z and estimate its error rates? And our idea is to construct Z from peer forecasters' predictions. Let's see this example. We have a set of prediction questions and a set of forecasters and their predictions. When we want to evaluate the prediction accuracy of agent 1, so we will generate this signal from other agents' predictions. So let's see. So for each question, we will generate a surrogate signal Z, and we first uniformly randomly select an agent. For example, for this case, we select agent 2, and then we draw Z being 1 with the probability equal to the prediction given by agent 2 points, which is 0.3 here. And we do this for each of the question. The property of this construction is that suppose each single agent has the same expertise level across all questions, then Z will also have the same error rate across all questions. This gives us a chance to estimate the error rates. And the method we use to estimate the error rates are checking the matching probabilities. And the terminology here is the method of moments. So we're considering focusing on 3 variable statistics that we can estimate from data. First is the frequency of a single draw of Z turns out to be 1 on a single question. The second is the frequency of a double draw of Z turns out both to be 1 in a single question. And the third is the frequency of a triple draw of Z on a single question all turns out to be 1. So this frequency can be estimated from data because we have multiple forecasting questions. And this frequency can be also expressed as a function of the error rates and the additional parameter P, which is the prior probability of Y being 1. So these all 3 variables are all unknowns, and we have 3 equations, and we have a closed form solution for this. So now we have complete our solution, the surrogate scoring rules. When we evaluate the accuracy of a prediction QI, we first construct the surrogate signal Z from peers reports. And then we estimate the error rates of this Z also from peers reports on all questions. And finally, we just need to apply the debiased formula. And the result is that we could get an unbiased estimate of the strictly proper score that we design, just as if we know the ground truth. And we tested our score on 14 datasets from 3 real-world human forecasting projects. Here, the y-axis is our SS score, and the x-axis is the true strictly proper scoring rules. And we tested 3 different strictly proper scoring rules. So we can see that SSR score recovers all true scores with a strong linear relationship. So now we have finished the question about how we can incentivize high quality predictions. And now let's consider the problem of how to generate accurate predictions from raw predictions. The problem formulation is very simple. We have predictions from a set of human forecasters on a set of forecasting questions, and we want to aggregate these predictions into a final prediction for each question. And an example solution is the mean. We ask that can SSR help improve the aggregation accuracy? Because we knew that SSR reflects the true accuracy of forecasters. And if we select top forecasters on each question and then aggregate over them, will this provide better results? And we also want to know how this method compares to other aggregation methods. And we conducted empirical study to answer these questions. We tested on 14 real-world forecasting datasets The questions cover a wide range of topics, including geopolitics, economics, and guessing the artwork process. And we focus on the metrics of the mean square error. And in our experiments, our method is to first compute SSR for each agent and select the top 10% forecasters, and then apply the mean aggregation. And the 10% is just an empirical choice here. And for benchmarks, we select 4 typical aggregators. For the sake of the time, I will just introduce the inference-based benchmarks. The others are also very popular because of their simplicity and robustness. The inference method, similar to our algorithm, when generating the prediction of a certain question, they will also use the predictions on other forecasting questions. Basically, they establish a probabilistic model and then estimate the ground truth as the model parameters using all predictions. Now let's first see the performance of these benchmarks. This table shows the mean squared error of benchmarks on 14 datasets. Red marks the worst one among 4, and the bold marks the best among the 4. We can see that each benchmark performs quite well on some datasets, but very bad on the others. There's no one-for-all method. This also reveals the difficulty of forecasting aggregation without ground truth. So if we look at the performance of this variational-based method, we can see it has almost perfect prediction on these 2 datasets, but worse than random guess on these 3 other datasets. So let's see our performance. The green marks the dataset where we outperform all benchmarks, and the yellow marks the dataset where we rank the second best. So we can see we are either the best or the second best among these benchmarks. The only exception is H2, but we can see the difference between the best one is very small here. So this demonstrates that our algorithm is both accurate and robust. Yeah. So yeah, may I know how many time I have? Hello?
It's
hello?
4 minutes.
How many minutes do I have?
3 to 4 minutes.
Including question or not?
No, not questions. That allows us time for questions afterwards.
Oh, okay, that's great. Okay, thanks. Yeah. So now let's compare our methods with the inference method. So both methods, because both of our method and the inference method use cross-task information in the aggregation. Basically, when we're generating the prediction on a single question, we will use the predictions on other forecasting questions. So that's the similarity between ours and the inference-based method. And the difference is that we use the information to identify the top forecasters first, and then apply the simple mean aggregation on these forecasters, while the inference method directly infers the outcomes. So if the inference model does not capture the data, they will perform quite bad, like in this 3 dataset. And it's very hard to tell whether the model capture the data in advance, because it will involve the knowledge of the ground truth. And we can see here, so even in this 3 dataset where the inference method performed quite bad, we still achieve very decent performance. And on the 2 dataset where the inference-based method are perfect, we still have a huge improvement compared to other benchmarks that do not use cross-task information. So this shows that our approach, which first infer the top forecasters using the peer prediction method, and then use the simple aggregator, will achieve both accuracy and robustness in the forecasting aggregation. So this also inspires us to use to test other peer prediction method to pick top users and do the aggregation. Yeah, other peer prediction method focus on eliciting categorical answers, like yes or no answers, but we find a way to adapt them to accept probabilistic inputs, and they achieve similar aggregation performance as our SSM surrogate scoring rule method. Yeah, cool. I think that's almost all about my talk, and I will briefly wrap it up. So in this talk, we focus on the forecasting scenarios where no ground truth information is available. And we address the forecasting elicitation challenge by proposing the surrogate scoring rules, one type of peer prediction mechanism. It reflects the forecaster's true forecasting accuracy, even without knowing the actual outcomes. And for the forecasting aggregation problem, we found that using peer prediction method to find out top forecasters and then applying mean predictions give a better trade-off between accuracy and robustness. So if you apply this kind of aggregation method, you will hopefully get a much better forecasting accuracy. Yeah. Okay, so that's about my talk, and any question is welcome.
Do we have any questions for Mr. Wang? So are there any limitations in these types of algorithms?
Yeah, so the limitation, the main limitation here is that we heavily rely on the assumption that an individual has the same expertise level across different forecasting questions. So usually when we apply this kind of algorithms, we should apply to a set of forecasting questions of the same topic. For example, when it's about replication, about forecasting the replicability of papers, then I think, and all papers are psychology, and I think these are reasonable assumptions. But if we mix different type of questions, then possibly the assumption that individual has a constant expertise level across different questions will be violated, and it will not perform well in this case. Yeah.
And have you tried these now with real data for a significant amount of real data to feel comfortable?
Yeah. So in my slides, we have already have some real data. For example, in this, we compare 14 forecasting data sets, and these are the real data of the geopolitical forecasting and kind of economics forecasting. We can see our scores are highly correlated with the true scores. So by theory, if the constant expertise levels assumption is satisfied, then this parameter should be 1 because they should be equal. But we still have a little bias here. So, but this is still very strong correlation. So we can reflect the actual accuracy of the forecasters even without knowing the ground truth. And these are also the about the real data on different forecasting projects. And these are the mean square error ranging from 0 to 2. And any number below 0.5, meaning that it's better than random guessing, than always guessing, making a prediction of 0.5. Yeah, and we can see on some data that we have very small, prediction error. Yeah.
And where does your research go next?
Yeah.
In this.
Yeah. So I think my next research goal is maybe to find some a more systematic way to estimate the accuracy of forecasters without knowing the ground truth, because in our current research, we still want to maintain the method algorithms satisfy the truthfulness property, but these are not required if we just want to do the aggregation problem instead of the elicitation problem. So if we drop these requirements, then I think there could be some other sophisticated method can be applied to identify top users and then doing the aggregation over these top users. So that will be a promising approach, I think. Yeah.
Thank you. Do we have any other questions? So with that, We thank you, Mr. Wang, for a wonderful presentation. And we'll go on to our next one. All right, so now I will go through the process of coming off so somebody else can come on. Okay, so now for our third and last presentation, I have Mr. John Grimm from Verizon. His talk is going to be private breaches in the cyber threat landscape. Mr. Grimm has spent over 19 years leading investigations of data breaches and cybersecurity incidents within the government and civilian sectors. Currently, he heads the research, development, and innovation effort within the Verizon Threat Advisory Center. Prior to Verizon, he served 12 years with the U.S. Army as a counterintelligence special agent, investigating security incidents in government and educational sectors and offering solutions to better mitigate, detect, and respond to cyber threat actors. So with that, Mr. Grimm, thank you for your service. Let me say that. And please begin.
Okay, thank you very much. Can you hear me okay? Okay, so let's go ahead and start. So thank you for the introduction. My name is John Grimm with the Verizon Threat Research Advisory Center. I'm going to talk about the cyber threat landscape here today, and in particular, a project that we're just wrapping up currently in terms of data privacy exposure. So looking at what's happening out there in the land of data breaches. So I've been with the team for 12 years, as I was introduced, doing digital forensics investigations, most of that time leading a team of investigators. So I'm going to bring some insight from the standpoint of what we see in our caseload, as well as what we're seeing in the Data Breach Investigations Report caseload, which is our flagship publication. We affectionately refer to it as the DBIR. It's the 14th year of publication. So for this particular discussion, we're going to talk about data privacy exposure, looking at 3 years worth of data within the 2018 to 2020 timeframe. We're looking at data breaches from the standpoint of confirmed breaches where there's been an exfiltration or compromise of data, meaning the confidentiality attribute of the CIA triad, confidentiality, integrity, and availability, is impacted at 100% of the time. So how do we define privacy data? Well, we're going to look at personal, medical, bank, payment, and credentials. I'll have more on that shortly. Looking at a total of 5,180 privacy breaches where those 5 data elements or data varieties were impacted. And we're going to look at this through the Veris A4 threat model, more on that shortly as well. And of course, offering countermeasures and controls in terms of the Center for Internet Security, Critical Security Controls version 8. So let's get started here. What is the data? So the 5 data elements are bank, personal, payment, medical, and credentials. Now, roughly the banking equates to your account information. So there's personal data there. Personal data, the way we define it, is equivalent to the PII, personally identifiable information. Payment data is equivalent to your payment card industry or your PCI data, associated data with your credit cards. Medical is PHI, protected health information. And then credentials can also be considered personal data or privacy data. So when we're looking at the 2020 timeframe only, looking at 2,271 data breaches, where again, we have confirmed that there's been a compromise of data, specifically here, privacy breaches. You can see in the chart here how the data stacks up. 91% of the time, 9 out of the 10 times we're dealing with personal data, followed by the credentials at 30%, your PHI at 19%, your banking information, your PCI data at 13%. Okay, so let's move forward here. So what industries are most impacted when it comes to privacy breaches? Okay, so now we're looking at a 3-year time frame, looking at 8,984 breaches where we've confirmed that privacy data has been compromised. So looking at the orange bar and comparing it to the gray bars. The gray bars are breaches in general. The orange bars are privacy breaches. So for example, healthcare, we have 886 privacy breaches out of 1,182. occurring in that 3-year time frame. So top of the list here, when we look at overall numbers, it's healthcare, followed by financial and insurance at 814, information, which is more aligned with media in terms of that category, at 519, professional services at 490, and public administration, which is government, at 389. So if you're wondering what healthcare parentheses 62 means within the chart, that is 62 code, the North American Industry Classification System. It's how we classify industries within the DBIR, and for today's presentation. When we look at frequency in all breaches, we get a little bit of a different story here. So now we're looking at percentages. So entertainment leads the way at 81%, accommodation at 80%, and there we see financial at 75%, followed by healthcare statistically right behind that at 75%, and real estate at 70%. Bottom line is all industries potentially have privacy data, employee data, customer data, and they need to be aware of privacy breaches. But you can see some industries dominate others in terms of overall frequency as well as overall numbers. So let's look at some timelines here. So time to compromise and time to exfiltration. This is from the attacker standpoint. And if we look spanning from seconds to years for both of these timelines, we can see that for the threat actors, it's rather quick to compromise privacy data and exfiltrate privacy data from the victim organizations. Now, this is for a 3-year time frame. Minutes, generally speaking, for time to compromise, half the time, and minutes, generally speaking, for time to exfiltration at 49%, almost half the time. So rather quick there in terms of the timelines. When we look at the defender timelines, the time to discovery and time to containment, it's a bit of a different story. And this is very similar to what we see in overall breaches, where it does take the defenders to detect or discover the breaches a lot longer than it takes the attackers to compromise and exfiltrate the data. In fact, you can see containment also takes a bit of time as well. So generally speaking, we're talking days at 32% there at the peak for time to discovery, and days at 47% of the time for the peak there at time to containment. But again, it really does depend on the nature of the privacy breach. It can take anywhere from hours to months in terms of the discovery, as well as hours to months in terms of the time to containment. So a lot of time can occur between the exfiltration and the discovery. A lot of damage could have occurred and happened in terms of what the threat actors are doing. Again, what we're looking at here too, to reiterate, is breaches. So these are the successful threat actor activities where they've been able to exfiltrate data. We're not actually looking at the incidents where a breach may be not fully fulfilled, or we're not even looking at events that didn't become an incident or breach. We're looking at the successful threat actor activities. On the bottom left here, for example, and you may have noticed this, the key sys controls, these are Center for Internet Security Critical Security Controls, or the sys controls, version 8. So see, these are some of the ones that we've identified that align with the particular slide. In this case, sys 8, 10, 13, and 17 as controls to better defend against these threat actors, reduce that discovery time, and improve the containment time, in particular with incident management or incident response management. Okay, so let's look at discovery. So discovery was the third timeline. Discovery is the first timeline from the defender standpoint. How are defenders discovering privacy breaches? Okay, so this is looking at the 1-year time frame. The yellow bars indicate 1 year, the dark orange indicate 3 years. So we're looking at the most recent data for last year. Actor disclosure is number 1, and that's an external discovery method, and it's at 53%. So what is actor disclosure? Well, it could be a ransomware breach involving privacy data, where the actor is disclosing that there's a breach through the use of a pop-up note for the ransom, or contacting the victim organization, or even bragging about the breach perhaps on a dark web forum. So actor disclosure is number 1 in terms of privacy breaches. Security researchers are number 2 at 19%. This is also an external discovery method. These are academia that's discovering configuration errors or vulnerabilities, and it turns out that there was a breach behind it. In this particular case, we're talking about privacy breaches. Security researchers also include service providers who may be offering a security solution to a particular potential customer, and they're letting them know that they've noticed that there's a configuration issue with their web application or a configuration issue with their cloud, and it turns out there's actually a breach behind that. Next on the list is law enforcement at 8%, also an external discovery method. Law enforcement may have a case looking at fraud involving privacy data, and it turns out that a particular organization is part of that case. They've been compromised and law enforcement is notifying them. Customers at 6%, maybe they're seeing identity theft in terms of their privacy data, or maybe they're seeing on their credit card statements that there's been a compromise, so at 6%. The top 4 discovery methods here are all external to the organization. So external entities are discovering these breaches before the internal entities or even the partner entities are discovering these breaches. Reported by employees at 4%, that's the first time that we actually see an internal discovery method. So let's look a little bit more into the data. Okay, so let's use the Veris A4 threat model to do this. Veris is the vocabulary for event recording and incident sharing. It's a common framework, a common language, a lingua franca that we use for developing the DBIR. We use it to actually collect the data, codify the data, and then pivot off of for the analysis for today's presentation as well as for the DBIR itself. So the A4 threat model is a core component to Veris, and it is the actors, actions, assets, and attributes. So these 4 A's form the A4 threat model. You can use this for your threat modeling in your organization. We use it to also explain what we're seeing within the DBIR from the standpoint of these 4 A's. So actors, there's 3 categories, actions, 7 categories, assets, 5 categories, and attributes, 3. So let's look a little bit closer at these. When we're getting into the actors, it does help to understand their motives. So before we look at who the actual actors are for that first A, these are the motives and privacy breaches for the 3-year time frame. And you can see that financial dominates at 94% of the time. And ultimately, if you do read the DBIR, you'll see that financial is the #1 motive overall, with espionage #2. But here we're looking at privacy breaches, and we're seeing financial at 94%, and then very, very distantly, at 2% each, convenience, grudge, and ideology at 1% each. So clearly we can see for privacy breaches, there is a financial motive behind it, and espionage is there at 2%, but it is actually in 3rd place statistically behind fun. And fun is actually not just fun and messing around, it's also exceeding your need to know. So if somebody's peeking at a patient's records and they're not the attending physician, then that would be a privacy breach or a compromise of privacy data because they did not have the need to know. Now, if we want to look at motives from the standpoint of internal actors, and wick away the external actors as well as the partners, we get a bit of a different story here. Financial certainly does dominate at 66%, but it is significantly lower percentage-wise than the 94% for overall threat actors. Fun then jumps to 16%. And convenience is at 10%, grudge at 5%, and then espionage is at 4%. So we get a little bit of a different story here when we look specifically at internal actors in terms of privacy breaches. Okay, so the first A, actors. So on the top, what we're seeing is actors and privacy breaches. These are the categories that we have within the DBIR, more specifically within the Veris framework: external, internal, and partner. And then there is some collusion sometimes, or some overlap where there might be multiple different types of actors involved in the same privacy breach. So external actors, as you can see, dominated 63% of the time, which does parallel what we're seeing in overall breaches in the DBIR, although the frequency is much less than this year's DBIR at 63%. Internal actors are a bit higher than the overall DBIR data set at 37% when we're looking at privacy breaches here specifically. Now, this is helpful to know, and it's good to know if the threat actors are coming from outside the organization, inside the organization, or a partner. But what's more granular, what's more informative is understanding who they are more specifically from the standpoint of variety. So the top is the categories. The bottom chart here is the variety. So this is looking underneath each one of those categories. And as we look at this, we can see #1 is an external actor variety, organized crime at 59%. And that makes sense because a lot of times when we're looking at organized crime, there's a financial motive behind that. Financial motive dominates privacy breaches. If they compromise that privacy data, they can cash in on it, monetize it, and make a profit. System administrator is #2. This is an internal actor variety. It's at 11%. Okay, and these threat actors could be nefarious in what they're doing, or they could have maybe committed an error and led to an exposure of privacy data. Unaffiliated, we switch back to external actors at 9%. These are threat actors who are not affiliated with organized crime groups or not affiliated with nation state or state affiliated groups, which we also see, and you can actually see state affiliated, it's at the bottom at 1%. Nation state is not on here. It's not in the top ones that we're listing here, but that is also a threat actor that's external that we often see in our data set, mainly with espionage breaches, as are the state affiliated. And then we can see end users that are there at 8%, internal actors, okay, that are leading to a data breach through their very actions. And then finally at 5% are your developers who are perhaps committing an error and it leads to an exposure of privacy data. So these are the actors. These are who are affecting the assets. Let's look at the actions to see how they're affecting the assets. So we've got a long list of syscontrols on the left-hand side of your screen. But let's look at the actions from the standpoint of the top level categories first, and we'll then look at the variety. So there are 7 action categories in the VERIS framework, or more specifically, the A4 threat model, okay? And what you're seeing here are 6 of them: hacking, error, social malware, misuse, physical. The 7th one is environmental. It was statistically insignificant for this chart, so I did not include it. But what we have is the top 6 out of the 7 here. Hacking is at 41%. These are the actions of the threat actor. They are taking steps to gain access into the environment or move laterally and exfiltrate data. Error is at 30%. Okay, so to kind of put this into perspective, hacking is typically going to be an external actor who does not have legitimate access to the data, the assets, the environment. Error is somebody that's making a mistake. They do have legitimate access to the data, the assets, the environment. They're either an internal actor or they're a partner actor. They do not have a motive. They are simply making a mistake. They are misconfiguring something, or they're misdelivering an email to the wrong recipient. It leads to a privacy breach. So they're at 30%. Social is an action that's typically seen by external actors who are socially engineering their way into the environment. Perhaps it's an email with phishing, or maybe it's pretexting or telephonic pretexting where they're calling them on the phone and not using an email or smishing or text message, for example. Malware is number 4, which is interesting because we would typically see hacking, social malware as the top 3. Here we see it as number 4 because error is a big significant part at 30% of privacy breaches. So malware is the action of the malicious software at 13%. And then misuse, this is an action that's aligned with an internal actor or a partner actor. They have some trust or privilege and they're misusing or abusing it. Could be their credentials, could be the hardware, it could be the software, even the data. And then finally, a physical attack at 4%. Examples of those would be payment card skimmers for the PCI realm, where it's a physical attack and not necessarily a logical attack into the environment. So these are the action categories. If we look below this, we're going to see the action vectors in privacy breaches. So this should make sense when we're looking at things such as hacking at 41%. Well, what's the vector? The top vector here is 45% for web applications, and that makes sense for hacking. When we look at errors, carelessness is a vector for the VERIS framework at 30%. This is the errors, this is the misconfigurations, the misdeliveries, and there's a whole slew of other potential errors out there. And then at 20% is email, which is a social vector that aligns with the social action variety. And then finally, if we look one layer below the categories and we look at the varieties for actions, and there are really dozens of varieties underneath all 7 categories. Each one of these actions has a number of varieties underneath them. So we're just holistically looking at the overall action varieties and privacy breaches, at least the top 15 or so that are right here from 2% or above. So we've got a range looking at the top there at 30%. Down to the bottom there at 2% in this particular chart on the right-hand side. So use of stolen credentials, which is a hacking action variety, is 30% of the time within privacy breaches. And use of stolen credentials is pretty high in terms of overall breaches. It typically will be at least in the top 2. And currently in this year's DBIR, phishing is number 1, followed by use of stolen credentials. Phishing is a social action variety. So use of stolen credentials, what does that mean? Well, first and foremost, where do those credentials come from? They come from that same attack. They come from a previous attack. They come from a previous attack by another attacker that's selling those credentials to the current attacker, or perhaps they're harvested from a fake website. it's particularly effective. And you can see here, 30% of the time it leads to a breach. Why? Well, they can get the stolen credentials if there's single factor authentication at play and not a second factor, something you are versus something you have and something you know. Something you know is the password. If you add a second factor of something you have, like a token, or something you are, like biometrics, you're going to really significantly mitigate the use of stolen credentials. But it's effective because some organizations are still struggling with implementing two-factor or more authentication. Also, users tend to use the same passwords a lot of times across multiple accounts or similar passwords. So this really does play into the use of stolen credentials, where the threat actor harvests those credentials from a fake website, tries those same passwords out in terms of gaining access into the enterprise environment and finding success, or they're using it for their brute force attacks, where the similar password is being used for part of the brute forcing, which you can see brute force is 3% here on the chart. Phishing is a social action variety at 18%. This tends to be the initial vector into privacy breaches, as well as data breaches in general. It's one of the options there if the threat actors are not going to use those stolen credentials. They're going to leverage the human element. Misconfiguration at 12%, that's your error. Misdelivery at 12%, that's also your error. This is the burger and fries of error, misconfiguration and misdelivery. In fact, those two combined for overall data breaches for this year's DBIR at 17%, but you can see here they're 24% combined. And then we get into a misuse action variety. Again, this is internal actors or partners at 6%, is privilege abuse. And then we get into ransomware at 5%. Ransomware is a big factor now with privacy breaches. In fact, ransomware is a big factor with breaches in general. This is the first time we've seen it at 10% of overall breaches in the DBIR. And you can see here for action varieties and privacy breaches for the 3-year time frame, it's at 5%. So not only are you dealing with the encryption from ransomware and also the exfiltration of data with ransomware, but also that data that's exfiltrated has privacy data within it. So you've got to deal with notifications from the standpoint of employees, customers, as well as regulatory requirements for those notifications. Okay, so quickly, let's move into assets here. This is the third A.
John, we have about a minute.
Okay. Okay, let me just roll through here real quick if we got a minute. So assets and privacy breaches, we are looking at servers primarily, web application servers at 46% of the time. When we're looking at attributes, confidentiality is going to be pegged at 100%, and that's shown in the data varieties that I revealed earlier. Alter behavior and software installation are the top two integrity attribute varieties at 53% and 43%. Alter behavior is the flip side of social breaches. Software installation is the ability to install software. And then finally, when we look at availability for privacy breaches, loss is at 51%. That's loss of an asset, and it leads to a compromise of the privacy data. And obscuration at 44%. A lot of that has to do with ransomware breaches. So in terms of the way forward, key findings, motives, internal actors and external and partner actors are all built around financial motive, with fun at 16% for internal actors. Discovery is actor disclosure at 28% and security researchers at 16%. When we look at the A4 threat model, we're talking about organized crime at 59% in terms of top actors. And when we're looking at the top actions, it's use of stolen credentials and phishing. Finally, top assets were web application servers, and then the mail servers at 46% and 33%. And then when we look at the integrity attributes, it's alter behavior 53% and software installation at 43%. So interestingly, here's the, if you're interested in the critical security controls for key privacy, I've highlighted these here in orange here. These are a total of 18 critical security controls. We recommend all 18, but hone in on these orange ones here. And if you're interested in Veris, here are some resources for the Veris toolkit. So that brings us to the end. I think we have some time for some questions.
Thank you very much. Do we have any questions? I actually have one. When you took a look at the data, is there any geographic slant to that data?
That's a good question. We didn't look at it from the standpoint of geographic slant, but there very much could be. In the DBIR itself, we do break the DBIR down into North America versus APAC versus EMEA, and there are some differences for overall breaches. But in terms of privacy breaches, one of the factors there for regional, when you're looking at EMEA in particular, is there is heightened reporting requirements for privacy data. So we would see a lot more of that because there's mandatory disclosure there. Whereas here in the United States and in North America, we're not, we don't have a federal privacy law such as the GDPR in Europe.
And do we have a view on cost of damage? In other
We
words,
do have some information on cost of damage in the DBIR on data breaches in general. We're looking at ransomware as well as business email compromise, but not split out for privacy breaches specifically. Again, this is all data-driven insight. We're not, we don't use surveys, for example, so we wouldn't have necessarily that financial impact.
thank you. Do we have any other questions for John? So hearing none. John, thank
Okay.
you very, very, very much for a very interesting topic and presentation. We really appreciate it. And with that, this is the last talk of this program. This concludes the program. And I'd like to thank our speakers and the attendees for participating in CEWIT 2021. All the attendees are encouraged to go to the main ballroom where they will be hear the closing remarks by Stony Brook University President Dr. Maurice McInnes. Thank you all for attending. We hope to see you next year at CEWIT 2022. And with that, I encourage you all to go to the main ballroom. Thank you again.
Thank you very much.
Ed Palacio. Bye-bye.